Okay, so what we're looking at here is work done through a voltage, and we could also call this voltage here an electrical potential difference. Electrical potential difference. Oftentimes we'll just hear this as a voltage or electrical potential, okay? But technically it is a difference. And what we're saying here is that a voltage is going to be equal to the negative work per some unit charge to it. And another way of thinking about this is this voltage here, because it is a difference, is a delta V, such that if we had some charge and we moved it through some change of potential, that would give us some amount of work. And this is a very similar idea to if you had a mass and you moved it through some potential, you'd be doing some amount of work, such as if this was flat ground and you had a mass here and you moved it up against gravity, this would be some height h you moved it through. This is a gravitational potential you've moved it through, and that gravitational potential, that GH right there, or GM over R if you'd like to think of it that way, would give you the potential, and you've put a mass in it, so that is a potential energy. Okay, and potential energy we know can be thought of as work. There's the work energy theorem. So that's all we're doing here. We're just saying, look, we've got a charge, an intrinsic property. We move it through some potential due to electric fields at this point, and that is equal to a work. And I forgot a negative here. That negative gets tossed in. Where we'd like to put it, let's just put it right here back on the W. Okay. In a prior video, we've talked about what that negative comes from and how we're thinking about this work here. And just like I said, if we think about this in gravity, this is equivalent to the idea of a change in potential energy. Okay, so that's what's going on with our little setup here. If we take a look at kind of an example, kind of like the most simple example of this, let's imagine for a second that we have two parallel plates. So here's a plate here, here's a plate here, and these plates are parallel to one another. And the first thing we'll think about is one of these plates is going to be charged positively. So let's just make this one on the left our positive plate, and the one on the right will have a lesser potential to it. So we can think of it as the negative plate. It may not actually be negatively charged, but what we talk about by that is saying, like, look, this is at 10 volts, and this one over here might be at 2 volts. So they might technically both be positive, but when we think about voltages, our higher potential is going to be thought of as our positive side of things, and our lower potential can be thought of as the negative sides. And the reason why we think about it like this is because, remember, electric fields travel from high to low potentials, which means that the electric fields are going to be pointing from left to right. And if I could draw these a little bit better, that would be nice. Here, we'll use the straight line tool again. So these electric fields are going to be directly like this, and I'll draw a bunch of straight lines first, and then we'll deal with moving these around. Oh, that didn't work very well, did it? What we're gonna have here is parallel straight lines going from the 10 volts to the negative 2 volts. These are all gonna have arrows on them because they're electric fields, and these are uniformly distributed. Okay. The electric field in between these plates is actually uniform. It doesn't matter if you're on the left or the right or the center or up here or here. The electric field is going to be a constant between these parallel plates. The only issue with that, and the only subset, is once you get close to the edges, you get what's known as an edge effect, where things kind of arc a little bit, and your electric fields will not be constant out on the edge there. But within the middle there, your electric field is constant. And when our electric field is constant like this, what we're able to say is that if we have some charge sitting, let's say here at 10 volts initially, and it winds up on the right-hand side at a final position, we can think about actually how much work is done there. The only thing we need to do is go back to our equation up here, Q delta V equals negative W, and think to ourselves, okay, well, what is our delta V? Well, in this case, remember, a delta is always a final minus an initial. So what is our final voltage here? Well, for some charge moving, it's 2 volts, minus, what's our initial, it's 10 volts. Okay? So this gives us negative 8 volts. That's our delta V, which oftentimes we'll just see written as a V. Okay? So voltage equals negative 8 volts. If our charge here is a positive charge, because it's moving with the electric field, positive or negative, then what we'd have here is, let's just say it's a test charge, or it's a proton in that case, the charge is 1 elementary charge, it would just be a positive E times negative 8 volts, and this would equal the negative of work. Now, as we easily see here, these negatives are going to divide out, and what we finally get as our true final answer, how much work is done here, is we have 8, and then this E is that elementary charge, but we can also think of it as the charge of an electron. So sometimes we'll say that this is an electron volt, and that is how much work has been done there. Okay? So that's it. If we had a flip side of this, if we had a negative charge, so let's say we started on the right here and then ended at the left, we're actually going to get the exact same answer. This would be our initial, this would be our final. What would happen here is we'd have 10 minus 2, which equals 8, and we'd say that 8 EV equals the negative work, and then that would just represent, or excuse me, this would, on the left-hand side we'd have negative 8 EV, because we have a negative charge here, equals negative work, and then once again we'd see that the negatives would divide themselves out. And that's because a negative charge is moving against the electric field, and this is the way it would want to move. Okay? When we have a positive answer here for the work, that means that the electric field is doing work. We're either moving with it for positive charges or against it for negative charges. If we ever get a negative answer here for our work, that means something, maybe you, are pushing charges against the direction that the electric field wants them to move. Okay? So that's what's going on with our little plus minus there. And that's just the most basic example of this. We can have more complicated versions, but anything more complicated than this, where the electric field is a constant, requires us to use a little bit of calculus and a little bit of fourth knowledge on what's going on there, or to at least know what the initial and final potentials are. If we know those, the rest of it doesn't really matter, but we at least need to know these two things, and normally parallel plates are the easiest way for us to do that. So not too bad there. Just one little equation for that, and just kind of thinking about how the electric field wants things to push. And with that, we are finished. Take it easy. Adios.